My name is Andrew Blakers from the Australian National University. The topic of my talk today is to point out that mass energy storage is a solved problem to support 100% renewables via off-river pumped hydro. This slide depicts global annual net new electricity generation capacity by technology. Solar, PV and wind won the energy race. Together they constitute about 3/4 of new generation capacity being installed each year. This slide shows the net new generation capacities installed in the years 2016 through 21 in gigawatts for all of the significant generation technologies. So solar and wind are growing rapidly. Gas is static, coal is falling, hydro is static, and nuclear, bio, solar thermal and geothermal contribute negligibly to net new generation capacity each year. In some countries, such as Australia, 99% of all new generation capacity is solar PV and wind. This graph shows the growing deployment of solar around the world, running from 2001 through 2021. Total deployment grew by around 500 times over the last 20 years and needs to grow by about another factor of 70 over the next 20 years in order to eliminate fossil fuels from the global economy. About 3/4 of the global population lives in the Sunshine Belt. This is the region plus or minus 35 degrees of latitude from the equator. This region includes most of the developing countries in the world which have high population growth and high growth in energy consumption and emissions. These regions have high and consistent solar energy availability and no cold winters. The supposed difficulties of reaching high levels of solar in an electricity system are mostly written from the point of view of Europe, Northeast Asia and Northern America. However, these constraints do not apply in the case of 3/4 of the global population. Although the winter sunshine at high latitudes is poor, there tends to be a lot of wind at high latitudes. And so everybody in the world essentially has either good wind or good sun or both. The USA has great wind. The redder the better. You can see that there's a lot of wind on the coast and a lot of wind in the center. The USA also has great sun. Again, the redder the better. There's a lot of sun in the southwest of the United States. It's world-class solar resource. Solar PV and wind are variable electricity suppliers. Demand and supply must be balanced for every second of every year in order to have a stable electricity system. There are several ways of ensuring that this occurs when a solar and wind dominated electricity system eventuates. It's very desirable to have both solar and wind. The wind often blows at night, and of course when it's stormy weather, when the sun is not shining, the wind is blowing. Often when it's calm weather, it's fine and solar PV is generating. Together they are better than either alone. A second method is to have wide geographical dispersion, preferably over millions of square kilometers. For example, the European Union or China or the continental United States or North America. This hugely reduces storage by smoothing out local weather and demand. The third method is demand management, shifting loads from night to day and incorporating interruptible loads, for example, an aluminium smelter. Finally, mass storage. Pumped hydro is by far the largest method of storage for the electricity industry, 97% of all storage. Batteries are becoming important and there are many other viable options. Transmission hugely reduces storage needs. Long distance transmission beyond about 800 or 900 kilometers is generally via high voltage DC cables. The state of the art for high voltage DC is a cable running at 1.1 megavolts over a distance of 3,000 kilometers, carrying 12 gigawatts of power with a 10% loss. The red line on the map of the United States shows that Texas wind power can be delivered directly to New York with such a cable or to the West Coast. A network of high voltage DC cables spanning the United States means that the amount of storage that's required to support 90 or 100% variable solar and wind will be reduced by a factor of 4 or 5. I'm going to spend some time talking about pumped hydro energy storage. The reason is that pumped hydro represents 99% of storage energy for the electricity industry and 95% of storage power. It's very likely that this will remain the case despite the rise of batteries, because pumped hydro is very cheap for overnight and longer storage compared with batteries. This is an example of an on-river pumped hydro system. We have an upper and lower reservoirs separated by 151 meters. This is called the head, 151 meter head. So water can flow down through those pipes to generate electricity, and at other times when it's windy and sunny, the pump turbines can reverse themselves and pump water back up to the upper reservoir. So water can cycle backwards and forwards indefinitely between the two reservoirs with a round-trip efficiency of about 80%. This means that about 20% of the stored energy is lost in a round-trip cycle. Off-river pumped hydro is an alternative, no river in sight. So this is a good example from Italy. The head, the height difference between upper and lower reservoirs, is now 500 meters. Similar water volume to the previous, with 6 gigalitres combined reservoir area of only 1 square kilometres, which is 19 times smaller, and it's got a gigawatt rating, power rating, and can run for 6 hours flat out. ANU's Global Off-River Pumped Hydro Atlas lists 616,000 sites all around the world, comprising 23 million gigawatt hours of storage. This is 1 million gigawatts for 23 hours, an enormous amount of storage, all outside national parks and urban areas. Roughly speaking, this is 100 times more storage than the world would need to support a 100% renewable energy system. The United States of America has 35,000 sites with combined storage of about 1.4 million gigawatt hours. This is about 200 times more storage than the United States needs to support a 100% renewable energy system. If you open the global atlas, you can zoom and pan to find the details of individual sites. So in this slide, we are zooming into Western United States and zooming further into the Denver region. As you zoom in, the individual pairs of reservoirs resolve themselves. This is a synthetic image of hypothetical 150 gigawatt hour pumped hydro storages in Texas. The upper reservoirs are light blue, the lower reservoirs are dark blue. The tunnel route connecting the two reservoirs is also shown. The dam wall is also illustrated in the lower right of the image. In these hypothetical pumped hydro storages in dry states such as Texas, the water goes up and down between the upper and lower reservoirs for the next 100 years. Very small amounts of water are required, much smaller than to operate an equivalent coal-fired power station. In our atlas, all the sites that are identified are outside national parks and other protected areas. It's important to understand that the reservoir area is rather small. To support a 100% renewable electricity system, only 3 or 4 square meters of land per person is required. The water requirement is also very small in the overall scheme of things. 3 or 4 litres per person per day is all that is needed to support a 100% renewable energy system, comprising the water for the initial fill, plus a small amount of water annually to make up evaporation in Australia's hot and arid climate. Many models have looked at the cost of balancing high penetration of solar and wind. Unfortunately, virtually all models fail to include the mature, abundant, low-cost, low environmental impact off-river pumped hydro energy storage technology. The consequences of this are that the cost of overnight storage is inflated, the amount of destructive bioenergy required is also inflated, and immature technologies are included that require a lot of arm waving about future scale and future costs. This is not to say that pumped hydro will necessarily be overwhelmingly dominant in future storage markets. It simply means that if you're modelling a high solar and wind penetration grid now, you should model it on the basis of off-river pumped hydro because it is a now mature, viable, low-cost storage option. In the future, if something turns out to be cheaper than off-river pumped hydro, then that's good. It simply means that the model will have over rather than underestimated the cost of balancing, and the cost of energy will be lower than modelled. So let's have a look at the renewable energy deployment speed per person. This is the number of new watts of solar, wind or hydro installed each year for a bunch of countries. So the larger the bar you see in this picture, the more rapid is the deployment of new renewable capacity. Hydro is blue, wind is green, and solar PV is yellow. So Norway, Netherlands, Sweden and Australia are out in front of the pack, installing at 200 to 300 new watts per person per year. And this is about 10 times the global deployment rate per person and 3 to 5 times faster than the rate in the United States or China or Japan or the European Union. Australia is a particularly interesting case because it is physically isolated and it cannot share a variable solar and wind electricity across national boundaries as happens frequently within Europe. Australia is finding that balancing high levels of solar and wind is much easier than most people think. 99% of new generation capacity in Australia is solar and wind, and those states with more solar and wind have lower electricity prices because solar and wind is cheaper than coal, oil and gas. Australia is now the leading country in the world for solar generation per person per year, as shown in this slide. Not only is Australia installing solar faster than other countries, it has more installed solar, and its solar resource is about 50% better than in Europe. Combined, these means that Australia is far ahead of its rivals. In response to the rise of solar and wind in Australia, new Australian LNG infrastructure is being developed, and pumped hydro is leading the pack with 3 existing pumped hydro systems, 2 new systems under construction, and about a dozen systems under detailed planning and feasibility studies. The Snowy 2.0 system, for example, under construction at present, is bigger than all the utility batteries in the world put together on an energy basis. None of these pumped hydro systems entail new dams on rivers. Utility batteries are starting to make significant inroads, destroying the market for gas load following. And new transmission is becoming ever more important to connect states to states, to smooth out local demand and weather, and also to bring new solar and wind from renewable energy zones into the cities. As an example of development of no new dam pumped hydro, Consider the Snowy 2.0 system under construction in Australia, 350 gigawatt hours of energy storage for about $5 billion US. This combines to produce a capital cost of about $15 per kilowatt hour. This is far cheaper than battery storage for overnight storage, and the system will have a lifetime of 100 years or more. In summary, overnight storage is a solved problem. Fossil fuels cause about 3/4 of global greenhouse emissions. However, cheap solar and wind will provide most of the energy and greenhouse mitigation in most countries, and energy managers can allow investment in solar and wind with high confidence that there is at least one highly credible off-the-shelf storage solution in the form of off-river pumped hydro. There's 200 gigawatts of it installed around the world. It's got the majority of the global storage market already. There's an unlimited scale of off-river pumped hydro potential sites. It's much lower cost than batteries for overnight storage. It's got low environmental and social costs, low water consumption, and long lifetime of 100 years or more. So thank you very much for your attention. More information can be obtained from the website shown on the screen, and I'm happy to answer any questions that there are. Thank you.